Thanks.
Thank you. So welcome everybody, and this morning it's our pleasure to have Maddalena Ferragatta telling us about towards a modular bootstrap of non-rational Virasoro CFTs.
Thank you so much. Thank you for inviting me. So indeed, this morning I'm gonna tell you something about the search of non-rational Virasoro conformal theories explored through the modular bootstrap. And this project is a work in progress, partially done, partially a work in progress with my collaborators, Giunce Rong, Francesco Russo, and Balvarres, who are all in Crete enjoying the sun and the sea. So since this is a seminar joined with mathematicians, even there maybe not too many mathematicians in the audience, I want to briefly start by reviewing what two-dimensional conformal field theories are. Then I will use this to introduce what we mean by non-rational Virasoro conformal field theories, and then give you some motivations about why we started this study. So during this whole talk, I'm going to focus on unitary two-dimensional conformal field theories, so two-dimensional quantum field theories that are also announced with a continuous symmetry given by the conformal one. In a two-dimensional case, this is the Virasoro. The Virasoro algebra is an infinite-dimensional algebra given by two copies of SL2R. This is generated by the holomorphic and anti-holomorphic transformations on the plane. And indeed, we have SL2R, but also announced with a central extension C. We refer to it as central charge. So these are the commutation relations of our generators. In particular, on the Virasoro, we can classify the operators based on their irreducible representations, so under their conformal dimension and their spin. What are they? They are simply the eigenvalues of the generators and not bar, and they are associated to the dilatations or the rotations on the plane. So when we're talking about states in a Hilbert space on the plane, you should imagine them as in a finite distance from the origin. So the dilatations on the plane simply describe the evolution in time of the Hilbert space. Now, we can also have either other continuous symmetries rather than just the Virasoro one. In this case, we talk about the chiral algebra of our theory. And in principle, we can classify all the space of our theory based on this chiral algebra. There's a first distinction based on this chiral algebra that helps us to classify the two-dimensional conformal field theories, namely the number of irreducible representations of this chiral algebra. If the chiral algebra is a finite number of irreducible representations, then we talk about rational conformal field theories. Otherwise, non-rational. Let me give you an example of rational conformal field theories, since we're talking in this talk for unitary conformal field theories. If the chiral algebra contains only Virasoro, they've been completely classified. They're the unitary minimal models, and they have central charge less than 1. Example, Ising, tricritical Ising, three-state pots, and so on. But in the rational case, there are also other extended symmetry rather than only Virasoro. For example, we talk about, you maybe have heard about WZWs, cosette models, and so on. And the rational conformal field theories have been partially classified. For the non-rational case, the story is more complicated, but we still have cases, known cases, for both examples. So only Virasoro is chiral algebra or Virasoro plus extended symmetry. With this setup in mind, now what do we mean by non-rational Virasoro conformal field theories? They're unitary conformal field theories that have a normalizable vacuum. They have only Virasoro as chiral algebra. They are non-rational. They have a discrete spectrum and admit a torus partition function. Now, what is a torus partition function? Since it will be the fil rouge, during this whole talk, let me give a brief review it. The torus partition function is the generating function of our theory. It counts the states, classifying them into the irreducible representation of Virasoro, where C here, where is the pointer here, is the degeneracy of the states in our Hilbert space that have the same conformal dimension and same spin. How do we obtain it? Where it is a standard procedure, we're gonna go with a conformal map from the plane to the cylinder. Now, on the cylinder, the Hilbert space is placed in the circles on it, and the time now evolves along the cylinder. We can then trace it to form a torus with modulus tau, and this is going to count for us the states in our Hilbert space and classifying them under Virasoro. A torus is invariant under two transformations called the modular S and T transformation. Namely, we can swap these two cycles, or we can rotate one by 2 pi, and the torus is going to stay invariant. This means, as a consequence, that the modulus partition function is going to be invariant under S and T transformation. Note that here the T transformation has a physical consequence, namely all the states of the operators have to be integers. Now, note that I've just used the word operator instead of states, because in CFT there is a thing that is called the operator state correspondence. Namely, we can, when we're talking about states in a Hilbert space, we maybe think about them as operators inserted in the origin. So this is why sometimes I abuse and I talk about operators instead of states. Now, with this definition, there is actually no known conformal field theory that has these properties. So first question may be, okay, but do they really exist? And this is the question that then started our work. And I can already anticipate you that answering to this question is a really hard problem. The results you're going to see at the end may not look too promising, but it is because it's really difficult and really there is no trusted conjecture on how to obtain them. However, it's not the first time that this question has been asked. Indeed, in the past 30 years, there was a conjecture that they may arise as putative fixed points of the RG flow of n-coupled minimal models, and that they should preserve part of the discrete symmetries of the RG flow. Of the UV fixed point. Now, on this conjecture, there have been done both perturbative and numerical calculations in the past 30 years, but it was with this paper of Doxenko and Nguyen and Santa Chiara in 2001 that for the first time it was highlighted the potential non-rationality of these fixed points. And then here in 2018 with Chang, Ling, Shao, Wang, and Yin, it was stressed out that they should preserve part of the discrete symmetry of the UV fixed point. Then last year, Antonio Antunes and Junche Rong tried to discretize this conjecture on the lattice. What do? They coupled n copies of the golden anion chain, which possesses Fibonacci as a symmetry. Now, don't worry if the word golden anion chain doesn't sound familiar to you, or the word Fibonacci, because on the lattice, we're not going to talk about it. And for Fibonacci, we're going to have everything clear in a few slides. On the continuum, their setup, and this is the important thing, corresponds to coupling n copies of either three-state pods of tricritical easing that are indeed unitary minimal models, and on the flow, it should preserve as a symmetry n copies of Fibonacci, semi-direct the permutation group that permutes these n copies, and then maybe times a discrete group that is a symmetry of the unitary minimal model, but it is very minimal model dependent. What they found is that even for the simplest case, so n equals 2, they claim that there may be a fixed points which associated to a conformal theory with central charge around 1.77. So this for us seems quite interesting, because what is this conformal theory? Because they were not able to identify it to previous known theories. This is what then started our work. So as a first step, we studied the symmetry for the n equal 2 case. So 2 copies of Fibonacci semi-direct permutation group that permutes these n copies. And then we decided to study it with a numerical modular bootstrap technique. Now, before going to the core of the talk, let me just explain you. When I say discrete symmetry, what do I mean about that? We use a modern definition. And for us, a symmetry operator is a topological defect line. It's a topological 2-dimensional 1 defect. When we're placing our theory on a torus, then it's a topological defect line. What does it mean being topological? If we're treating a conformal field theory, which has as a continuous symmetry algebra the Virasoro 1, then it means that it's really commutes with Virasoro. On the cylinder, we could think about as commuting with the translations on the cylinder. And what is the proper mathematical tool to describe them? Well, not groups anymore, but actually diffusion categories. And that's why I'm here, basically. So The core of the talk will be the following. In the first part, I'm going to review the fusion category viewed as topological defect lines. I'm going to briefly review them, then try to understand how we can insert them on the cylinder, and then what consequences do they have when we trace to form a torus? What consequences do they have on the partition functions? In the second part, I'm going to use the previous result then to implement the numerical modular bootstrap. Is it all clear? Yeah.
Can I ask a question? So with these fusion categories, is there a sense in which I'm guaranteed that this does not correspond to an extended chiral algebra? That it really is something where the algebraic structure, at least is when I'm trying to classify rational versus irrational, really is just Virasoro, and that this extra structure that you're having doesn't have that interpretation as being an extended chiral algebra? The question makes sense?
Partially, I would say. If I understood correctly, because I'm not sure, you can impose only Virasoro with a central charge greater than 1, a discrete spectrum, etc. And this is a continuous symmetry algebra. So it means that the currents in your theory, there will be only Virasoro as a current in your theory, right? And then on top of it, you're going to impose a fusion category structure, which has a finite number of elements. It's really you can think about it as the generalization of a discrete group.
Right. So with this discrete group, even though it's putting more structure on the theory, it doesn't actually correspond to having additional conserved currents.
No.
Okay.
No, indeed, because it's not continuous.
No.
Okay. It can't be generated by the conserved currents. Yeah.
All right, thank you.
Okay. So fusion category.
This does or does not change the character that I use? If the characters are still just Virasoro characters, even though I have this discrete
they are
symmetry,
just, yes. You're going to see how the partition functions change, but yes, indeed.
Okay.
You're going to act on them.
But everything gets scrambled. It's not like they go into nice representations because it's a fusion category, not a group.
Sort of, but they still have classification into just representations. We're going to see it. Okay, so what is for us a fusion category? It is a collection of topological defect lines that are oriented on the plane, together with a prescription on how they can fuse. Here, for example, lines I, J, and K. How do they fuse? Well, standard fusion, I'm going to write it in this way. So a line I fuses to a line J, and in principle, it can give all the possible lines of my fusion category. The delta I, J, K star are coefficients that can be either 1, if K can be obtained from the fusion of I and J, or 0, if not. In principle, these coefficients can have also higher multiplicities, but in this talk, I'm not going to talk about it. You should imagine them as just the lines that are dressed with colors, if they multiplicity higher than 1. But this will not be the case during the talk. Graphically, this fusion corresponds, so if a line K can be obtained from the fusion of I and J, this corresponds to this trivalent vertex that should be read counterclockwise, where the line I and J are ingoing and the line K is outgoing. These lines in the fusion category language are called simple objects of the fusion category. And by definition of the fusion category, there is always the identity that graphically corresponds to no line at all, because it acts as a standard identity in group theory. So what happens if a line I fuses to another line to give the identity? So no line at all. Well, we represent this line that fuses to I as I star. It is called the dual of I. It's unique, and by the existence of this trivalent vertex, it can also be represented as the line I oriented in the opposite direction. Now, maybe you can see what it's written here, but doesn't matter. So when the line I fuses to the line I star, it can give the identity, but in principle, it can give also other contributions. That's why in general, for this fusion category, we talk about non-invertible symmetries. Because in the case of a group, this is just the inverse element. Then, to every line I, there is a number associated to it, the quantum dimension di, that for us physicists, it can be just interpreted as the vacuum expectation value of this line I. It is represented as a loop of the line I, and in correlation function, it simply means that if a line I does not wrap around any operators or around any other cycles, it can be simply replaced by the quantum dimension times the identity. Also, the quantum dimension satisfies the diffusion rules. And I'm going to say, but I'm not going to prove here now, that the quantum dimensions, if the theory is unitary, are greater or equal than 1. Now, we can play some games with these lines other than just having equivalent vertices for loop. But to evaluate them unambiguously, we need a normalization. It's standard to pick as a normalization the so-called bubble move here. Moreover, the fusion categories are the fusion rules are associators. So every fusion category comes with a set of associators, the so-called F symbols, that allow us to resolve with so-called F moves. Let me do an example in the simplest case that is not a group. So the Fibonacci or fifth category. It has 2 lines, the identity, so no line at all, it acts as a standard identity, and the tau line. The tau line has this non-trivial fusion. So it fuses to itself, giving either the identity or the tau line itself. As you can see here, tau is self-dual, and therefore, because of the orientation reasons, it can't have any orientation. And moreover, its quantum dimension, if one resolves the fusion rules, is simply given by the golden ratio. So here I've put just the non-trivial F symbols of this category, just because I want to tell you how easy it is to obtain them. How? Well, we can bootstrap them. Let's put here some coefficients A, B, C, and D. Then we can contract the external legs, impose the bubble move, the correct normalization, and that's it. We're going to obtain them. So this is all I wanted to tell you on the plane. Now, conformal map, and we can go to a cylinder. We can put a conformity theory on the cylinder, and we can ask ourselves about all the possible lines that we can insert on the cylinder. Example, we can insert a simply vertical I line. What does it do? Well, it is gonna go in the inverse space, and it's actually gonna twist it. It's gonna modify it. Therefore, the inverse spaces, when there is inserted a simple line I, are gonna call twisted I inverse spaces. But actually, if one thinks about other networks that can insert, it turns out that there is a basis. And this basis is given by the so-called lasso maps, here drawn in this way. And this, for example, is a lasso map, but they're in maps, so they go from I inverse space, in this case the twisted I, to the twisted inverse space. Why are they particularly interesting? Well, because they satisfy an algebra, the tube algebra. And in the next slide, I'm going to go for a second in the next slide to show you how we can obtain this tube algebra. Now, you don't have to follow the computations. I just want to tell you how easy it is indeed to obtain and show you an example of a computation for this algebra. So these lasso maps have to be read from bottom to the top of the cylinder. Therefore, applying 2 of them recursively corresponds to stacking 2 cylinders one on top of the other, and then reading the resulting mathrm from bottom to the top. Then we can start applying a sequence of F moves. And it turns out that if one applies 3 F moves plus a bubble move, so indeed a resolution of a bubble, then has a lasso map again. And this is just the algebra. So let me now go back to the previous slide and tell you what we can do with this algebra. Well, we can study it. And the simplest thing we can do is consider just lasso maps that act within the same inverse space. So here, S is the same of I. The tube algebra in a twisted inverse space form a closed subalgebra. We can resolve it and obtain, in the same way we do for groups, for discrete groups, the reducible representations of the lasso maps within the same inverse space. Here they're labeled just by gamma. We can then build the projectors into these irreducible representations. By some properties that this algebra has, it turns out that we can build these projectors in the same way as we do for groups. So here, chi is the character of the reducible representation gamma, and is just a normalization required that requires that these projectors square to themselves. In the TQFT fusion category language, sometimes they're called the minimal centroid and potents, but they're really nothing but the projectors into these irreducible representations. Once we have these irreducible representations, we can then divide our twisted Hilbert space into subsectors given by the reducible representations gamma. And what does it mean? That a state that is in this twisted Hilbert space that is also in this subsector will have the lasso maps that act on it being in the representation gamma. Okay. We can see an example for Fibonacci. Oh, it's a pity that this is a bit, but can we move Francesco away? Maybe not. Well, no, don't worry. Maybe I have to close this.
Yeah, try to see.
But I don't have my arrow anymore. See,
Okay,
it. Well, it doesn't matter. Okay. So Fibonacci, we have two Hilbert spaces. The untwisted, same as twisting with the identity. So we're not twisting actually. And the twisted by the line tau, because we have only two lines in this fusion category. In the first, so in the untwisted case, we can have two maps. One, all is identity, so no line at all. Second, only a tau line that wraps around the cylinder. And if one solves the subalgebra in this untwisted Hilbert space, turns out that this is just the algebra that is the same as the fusion rules. And solving it is going to give, for the tau line, two eigenvalues, xi, so the quantum dimension, and -1 over xi. There are two one-dimensional irreducible representations, and we can therefore split the Hilbert space into two subsectors. Now we can ask ourselves, okay, but where are our states, our operator of the conformity theory going to fit, in one or in the other? And therefore, where is the identity going to fit? Well, if a tau line wraps around nothing or around the identity, this is just going to give the quantum dimension. So for sure, in the first subsector of the Hilbert space, the identity is going to be. Now, let me go to the twisted tau. We have here three networks. The vertical tau is simply going to define our Hilbert space, twisted by the tau line. Then we can perform a 2-pi rotation and obtain this kind of lasso map, and then the lasso map with all the tau lines inserted. Now, let me just focus on a second on why we decided to label this not with an L, but with a T tau. Because a 2-pi rotation can be written also as e to the 2-pi I p tau, where p tau is the generator of the translations on the cycles of the cylinder. And on the plane, it just corresponds to the rotations. And therefore, we expect its reducible representations to be related to the spins of the operators in this Hilbert space. Okay, and indeed, if one solves the subalgebra in this sector, turns out that indeed there are three one-dimensional irreducible representations. The T tau is indeed associated to the spins of the operators. And turns out that they can have either integer spin, 2/5 plus in modular an integer, or -2/5 modular an integer. And this is going to divide for us the Hilbert space into three sub-Hilbert spaces. So when we have an operator with spin 250, it's going to be placed in the second sector, and so on, if one has all the operators in the twisted tau Hilbert space.
Isn't this a bit weird, spin 2/5?
Well, we are twisting with some lines, so...
Yeah, but what does this mean physically? How should I understand?
So you should understand that this is how I understood it first. So you place the, if you work then with partition functions, you place a horizontal tau line, you simply know that in front of your characters, you're going to have either xi or -1 over xi, depending on your states. Then you perform a next transformation, and you're going to go to the twist Hilbert space. The horizontal is going to become vertical. And then there, you're indeed seeing that the characters are going to combine such that when you do a small Q expansion, you're going to see that emerge three kinds of spins, so 0 to 50 minus.
You're not answering my question. Suppose that I perform some measurement of an observable. What does it mean that the spin is 2/5?
Well, for me,
The
this means that
correlation
it's
functions of this So this is supposed to be some local operators, so
Yes.
how can they be introduced?
Well, I don't think I never thought about being weird of having an operator in a twisted sector that can have you can take all
We
the
have never
spins.
heard about the fact that you usually have fermions, bosons.
No, sure. But this is if you have like a Z2 symmetry, for example, you start with a bosonic symmetry, then you are gonna insert the Z2, and you're gonna see that in the twisted sector, the fermions are gonna appear.
Can I ask a quick question maybe in a different way? So this is some sort of like anionic type of modes. So it's not a boson, it's not a fermion. It just has this kind of weird. Like, should I think about this as like anions? That's one question, and the second question is when I eventually put it into a torus.
Yeah.
I'm picking only one of those three values of L.
For the torus, we're gonna dive, and you're gonna see how it works.
Okay.
I'm gonna write next. For the first question, yes, indeed. They're not these simple lassomaps that are anions, but actually the projectors. So these linear combinations are going to be associated to the anions, what is usually one thinks anions. Okay. So these are just the projectors into this, because they're the projectors into these subsectors, the hyperspace. So you're gonna have here the projector into the Xi, the projector is to the -1 over Xi, and here the projectors into the three subsectors. However, we can also have lassomaps that act within different Hilbert spaces. And what does it mean? Well, suppose you have a state O that is in the twisted Hilbert space I, and a state O prime that is in the twisted Hilbert space twisted by S. Suppose also that there is a lassomap that acts on O, and it's going to map it to a prime. Now, to every lassomap, we can actually build a conjugate map. How can we do it? Well, it's a dagger operation. So we're going to flip the cylinder and revert the sign over the lines. Now, if a theory is reflection positive, then a dagger L is always going to be a positive semi-definite operation. And if a dagger maps O prime to O, so since they are topological, we have just built a one-to-one correspondence between states that have the same conformal dimension and the same state. This is the story for which for groups we usually in physics just consider a representative of a conjugacy class. Because linear combination of lassomaps allow us to build a one-to-one correspondence between a twisted Hilbert space twisted by an element of the group and the Hilbert space twisted by its conjugate element. Okay, and now we can see what happens instead in the case of Fibonacci. That is the simplest one. So we have one lassomap that goes from the untwisted to the twisted tau, and one lassomap that performs the opposite operation. And if one performs the conjugate, turns out that they are really conjugate, one to the other. However, it's not that we can take every operator in our Hilbert space untwisted and map it to the twisted and vice versa. First of all, because their spin and their conformal dimension has to agree. But second, because the algebra is telling us something more powerful. They have a non-trivial kernel. If one fits the lassomap that goes from the untwisted to the twisted with an operator that is in the first sector, so on which the tau line, the horizontal tau line acts with eigenvalue Xi, then you're gonna get 0. You can't go to the twisted Hilbert space. Otherwise, yes, if you take an operator that is in the second sector, you can. Twisted tau. If you take an operator in the first sector, so integer space, you can go in the untwisted. Otherwise, no. This also makes sense from the fact that they have their spin has to be the same, right? Well, if one is spin to fifth modular an integer minus to fifth modular an integer, of course, this is never going to be the same as the untwisted, where all the spins are integers. If one then performs L dagger and L dagger L, We know that they're positive semi-definite operation, but turns out that they really project us into these subsectors. So this one, where the tau line is -1/xc, or this one of the tau sector where the spins are integer. So all this algebra is telling us that there's actually a one-to-one correspondence between all the states in this Hilbert space and all the states in this Hilbert space. From the Virasoro perspective, they're really equivalent. Okay. Now, in general, for fusion categories, we don't have only a single sum up. We have linear combination of them that perform this correspondence. And usually the correspondence may also not be one-to-one. It depends on the dimensions of the reducible representations and on how the correspondence is realized. Okay. Now we can arrive to the partition functions to answer your question. So first of all, we can't have this kind of intertwining maps inside the partition function because we have to trace to form a torus, and therefore we can only have maps within the same Hilbert space or linear combinations of them. How are they going to be placed in a partition function where they're topological, they commute with Virasoro, and therefore they can be simply inserted in the trace? This is the game for L or also for the projectors. Now, these partition functions, Zi gamma, are really going to count the operators in Hi gamma, so in this subsector of the Hilbert space. They're going to classify them based on their conformal dimension and their spin. And it turns also out that by what I did for Fib, that is generalizable actually to every fusion category, all the spins in these subsectors are the same, modular and integer. So they are really the physical partition functions. They're the ones that are associated to the elements. However, there is actually, we're not quite to the anyons because there is only, again, one more thing. That is, where is the information given by the intertwiners gone? And it's here. It's in the fact that actually if two sub-Hilbert spaces are intertwined and there is a one-to-one correspondence, then the partition functions are the same. They're not independent. They contain the same information. Why this coefficient? Because indeed the correspondence may not be one-to-one. So in this case, we can have proportionality between the partition functions. So, but they're not independent. That's the main thing. And what are the consequences on the modular transformation on these new partition functions, where we can see it on Zijk. So here, the S transformation acts in this way, the T transformation acts in this way, and these new networks are actually not new. They can be rewritten as a linear combination of the previous ones with just one F move. And what consequences it had on the Zi gamma, or better, on the just the independent ones? If we put them in a vector, Z turns out that it transforms covariant under anti-transformation. This is an example for Fibonacci. So we had 5 sectors, 2 in the twisted, 3 in the twisted. There was a one-to-one correspondence, and therefore the independent sectors were only 4. So now you can see here just the 4 independent partition functions, indeed the 4 Fibonacci anyons. And you're going to see here the S and T matrices, where the T is indeed going to encapsulate the information related about the space. Now, what did we do? Fibonacci is quite easy, but we started from understanding it in the way I presented it, and then we did the study of 2 copies of Fibonacci semi-direct permutation group that permutes the 2 copies. It was quite tedious because there is not a software available for fusion categories as gap groups that allow us to do all this kind of computation, so we had to do everything by hand. The sectors were 52, not 5 anymore. We had to build all the intertwiners as linear combinations of the lattice maps. We arrived to 22 independent subsectors, or 22 independent partition functions. The correspondence was also not always one-to-one. But we had this gigantic system of these kind of equations, 22 by 22, with a 22 by 22 matrices, S and T matrices. And we use them to implement the numerical modular bootstrap. So now, if you don't have questions, I'm going to go to the numerical modular bootstrap part. Yeah.
So I didn't know anything about these fusion categories.
Yeah.
Someone just presented me with the data about the CFT and didn't tell me about any of this additional structure. Would the modular transfer, would I see that I don't get closure under naive modular transformations? That is the fact that things are scrambled up where S&T transformations also involve these non-trivial S&T matrices. Does that mean that in some sense the modular transformation itself is different?
Yeah, but you're going to get more like a set of partition functions for right all the Z I gamma. So what does it mean if one gives it to you for a single?
Right. If I did, maybe that's question, like for the naive partition function that I have that doesn't have these sectors. Is that thing not defined for this construction, or is there kind of a notion of the naive partition function that I would get if I were doing a standard modular bootstrap?
Well, it's an option that you put on top of that, because you can do the modular bootstrap just with the standard partition function untwisted, nothing, and then it is invariant under modular S&T transformations, right? Then if you start with it to like combine with all the others that you get, like twisting, etc., playing all these games, then in this sense you're gonna get a set of equations, and they encapsulate the information about the fusion category.
Right. So is it correct to think about all these additional partition functions that you have as kind of like having different boundary conditions for when I sew the ends of the cylinder together? Is that a reasonable way of thinking about like where these all come from? Kind of different choices that I have for sewing things together that are consistent with the operator structure.
I don't know.
Right.
I should didn't think about it in this way. Yeah. I don't know. I just thought it was dressing.
Okay, so I can apply the modular bootstrap to the standard, kind of naive partition function. Now you're going to tell us in the next part that you can also do this additional structure that appears when I look at these additional partition functions.
Yeah, precisely. Yeah. Okay. So the numerical conformal bootstrap starts to study 4-point functions in conformal theories. Slava, Ratazzi, Tony, and Vicky, and it takes as a constraint the invariance under crossing of the 4-point function, and it feeds it to a linear programming algorithm. Then Ellerman started the modular bootstrap, then instead is to study the spectrum of two-dimensional conformal field theories, so it takes as the partition function, takes as a constraint the modular invariance of the partition function, and gives it to a linear programming algorithm. It was then developed more by and improved by Collier and Yin, and this is an example of what they did. So you start by defining the twist of the operator as the conformal dimension minus the spin. They impose then a positive twist gap on all the operators outside the Virasoro identity model. What does it mean? That there can be any operators outside of it that can have the conformal dimension equals to the spin. So there are no other continuous conserved currents. So we have only non-rational Virasoro conformal field theories. They then plotted the twist gap, the results they obtained for the twist gap against the central charge. What usually one has in the numerical bootstrap is a disallowed region. This is a bound between a region that is disallowed, that can't have the constraints I'm giving it as an input, and a region that therefore can be allowed. As one improves the numerics, so for the expert, increasing the number of derivatives in the functional, the bound shrinks. It gets lower and lower, and they claim that it should hit C minus 1 over 12. Now, what is C minus 1 over 12? It is a strict bound that actually comes from analytics constraints. We then decided, so with this game, with no additional symmetry, to look at the low central charge part. And this is what we find. So this is the bound. This is how the bound improves, improving the numerics, so increasing the number of derivatives in the functional. As you can see, we're still quite far from C minus 1 over 12. And we see that there is a sharper region. what is this sharper region? Well, usually in the numerics, if one gets a kink on the bound, it may be a sign of a physical theory there. So having this sharper region is a nice feature, and this sharper region seems to get sharper and sharper as one increases the number of derivatives. However, we're still above the physical region because we know from analyticity that we should stay below C minus 1 over 12. So what happens when we go below is this.
Can you explain what's the difference between this plot, this analysis, and their analysis?
They didn't. They just plotted a straight line, and they said, "Yeah, it should converge to C minus 1 over 12." This is just what the information we have from their paper.
Yeah, but what about the equations that they? Because you spoke for a long time about more complicated equations.
Yeah, no. For this is the same kind of analysis they did. We just reproduced their stuff. So we at the beginning we're gonna do it just without adding any symmetry. It's just standard partition function. So we're just reproducing literally their numerics.
Okay, but your plots don't look like their plots. So what's?
Indeed, indeed. Yeah. I don't know. It may be because they didn't see it because they plotted a long range of center charge, right? We're just focusing between 1 and 2. And we're seeing this thing at really low levels of the central charge. But yes, right now, we're not doing anything different from what they did.
But what's going on? Why are your plots so?
That's a nice question that we're trying to understand. Yeah, we don't have answers to this shape. We only have questions.
No, I'm not talking about the shape. Why do you have like points all over the place? So usually you go from bootstrap, you get like.
No, right, no, because this plot is just because the bound of the allowed region. We should have cleaned it up. Right, we just we should have cleaned it up, but it's you should just look at this kind of one.
So all the points that you put are allowed.
Yeah.
This is how you should.
Yeah, you should think it is allowed, but I mean, I just plotted it for this is allowed. Should have been all. It's almost there, but.
I don't see how I do. Do you use the navigator? What do you use?
We use SDPB.
Which particular algorithm do you use?
We use it we use it there.
I'm surprised. Usually we don't see such plots because you just sit on some value of center charge and then you maximize and then you get just a point. But you seem to be like not maximizing, you're just trying points random.
Yes, we are not fixing the value of the center of charge.
It seems like you're using a little bit of a slow.
So we're not doing bisection. We're just so we're not fixing the value of the center of charge and then trying to find points. It is finding them randomly.
Yes, so the C minus 1 over 12 line, that's conjecture or that's proven? No,
it's proven. There were some conjecture. It was proven last year by Sri Page, Shin, Xiao, and Balbahes. And it's a bound at large spin. So there is a conjecture that all the operators at large spin should accumulate there. But since the twist doesn't care about the value of the spin, it should be a bound on the twist.
I see. So the fact that you're so far away from that line is saying that it's like super high, that bound is saturated by super high spin, and you just aren't seeing it because you're not taking enough derivatives.
Yeah. So with some extrapolations, it seems that at around 500 derivatives we should hit. But yeah, we're very far. Okay, so now we can.
You also say that there is a kink there.
We're still that there is a sharper region. What?
The kink would violate this one.
No, well, the point is that it should go below. It's just that our numerics is not that powerful. If it goes, our question is, if it goes below, right, like here, is it gonna do something like this? So is this kink gonna survive or not? Is it gonna move? Where is it gonna go? Is it gonna, maybe we don't have any information, maybe this is gonna flatten out just below C minus 1.
Have you tried just a single point okay, here you say, well, maybe it's not the range they looked at, but have you tried like one point which they also tried at the same exact value of lambda to see that you get exactly the same number as them?
No.
Sure.
Yeah. Yeah. Thanks for the advice. You're right. Okay. So this is weird. We're trying to understand it. Now let me tell you what happens for the numerics when we add the symmetries. Now the constraints we're gonna give to the numerics are gonna be this sum rules with this partition function Z that encapsulate indeed. So these matrices are gonna encapsulate the information of the fusion category. We're gonna give them free input in the modular bootstrap. So this was firstly developed by Lin and Shao. This is again Fibonacci. They also did Fibonacci. They didn't plot, however, they didn't study the twist gap against the central charge. So what happens if one has just the scalar gap is that if one finds a kink in this method, it seems that it's more likely saturated by a rational theory, because you can't avoid the fact that the characters may combine to give you a conserved current. So with this method, we're sure that we're looking at non-rational Virasoro conformity theories, and this is what we find. So this is the comparison between the case without symmetries in green and with Fibonacci in blue. So you can see that the bound improves, right, where it gets lower. And here you can see, well, how the bound shrinks and gets lower and lower as we increase the number of derivatives. We're still far from C-1/12, but this feature of the sharper region seems to survive. So what happens if one gets below C-1/12? We're trying to study it with some extrapolations. Of course, would have been nicer to be already below, but it seems the numerics is not enough powerful. This feature of having the sharper region that survives is not only associated to Fibonacci. We also tried other kind of symmetry as also Z2, Fibonacci there as Z2, and this sharper region seems to survive, but it's not the case for all the symmetries we tried. There is an example, and since we did the Fibonacci, well, 2 copies of Fibonacci. There is not. Even at low number of derivatives, we didn't push it more. That's what we're doing. It's all work in progress. But as you can see, the sharper region disappeared. So this is for sure an interesting feature that we're trying to understand. It's also way closer to the bound, to the C-1/12 bound.
Because you are plotting this tau gap, so tau gap is an unusual observable because it's defined in terms of operators of arbitrary high spin.
Yeah.
So
we're cutting the spin.
Do you have any idea if when you go to the boundary, so when you go to the boundary of this allowed region, at some spin, the operator is going to hit this tau gap.
Mm-hmm.
Even though you go this constraint at all spins, there's going to be a single one which is going to be saturated, presumably. It's unlikely that they will all simultaneously approach the gap. So do you know which is the spin which dominates this constraint? It's a
No,
natural question.
but I'm a bit confused because the twist gap is a an observable that is for all spin, and here it's like it's other way. You don't have you don't have constraints on the conformal dimension.
It is for all spin, but when you for all spin for all dimensions, but when you try to violate this bound, I'm saying that there's going to be usually the way these constraints are violated when you try to approach the bound is there's going to be a particular operator which is going to a single operator which is going to hit the bound.
Yeah.
And that operator is going to have a particular spin.
Yeah.
So so even though you talk about gap for all operators.
Yeah, you're right. Yeah.
Spins.
No, we.
It's a very natural question to ask.
Maybe
It's a very
I can just briefly say,
No.
I mean, if we do the spectrum extraction, we saw that usually it's the scalar again, but this is very preliminary. That with the spectrum extraction, it's very sensible to where the bound is. So this is just a preliminary thing. But I would say it's low spin. Low spins is dominating, is saturating the constraint.
I see. Thanks, Rob.
Yes, so technically when I'm doing this, so these are only one-sided bounds. I can't bound the other direction.
I'm not sure. That's just what I'm showing you. Of course, the other direction is bounded and it's closer. It's really closer. I just decided for clarity, since we still didn't clean these plots to do not present both bounds.
No, I think I'm asking the other direction. So it's based on the title of your talk, and looking for basically non-rational. I want the twist gap to be kind of bounded so that I can't get the zero.
But this is something we impose from the beginning. It's not.
So
I'm imposing that we're working with a positive twist gap. So I'm imposing that the twist gap is greater than zero. So I'm already sure that we're looking just at non-rational
forces that I can't. At what point did you force that I can't have any twist equal zero states?
We just simply impose it by hand. It's really imposing it by hand.
Because she wants that, she says if there is a state which has twist gap zero, then it's some extra conserved current.
Yeah.
And
I do one.
Maddalena doesn't want any additional.
I know you don't want. I know you don't want one. I guess the question is, does the bootstrap know that you don't want one?
Sure. Yes, we impose it. Yes.
Right, and I think I missed where did that appear? That is, can I get like arbitrarily close, like in the allowed region? Can I get arbitrarily close to
Yes.
to twist equals zero?
Yes.
Right, and then how do I exclude zero exactly?
We Francesco. I think we really put just we
No,
just
but-
Yes. So
just zero. It's
yeah, I mean, we just put the twist cap which is to be greater than zero, and so in this way we force the numerics not to create conserved characters, and so in this way we're ruling out for possible Virasoro currents. So when you're on the boundary of this blue region, for instance, you're forcing the characters to have a twist gap. And if they have a twist gap, you cannot form any conserved currents. And so in this way, the numerics, when you're trying to extract the spectrum in that place, you see that the spectrum indeed is what we're plugging it in. So there is no conserved currents at all.
yeah. Yeah, it's the same. Okay.
The strategy was not clearly explained, Lucy, but do I understand that they want to find this irrational CFT, so you say, let's just impose this gap, and then let's go to the boundary of the allowed region. If there is like a special point on this boundary, that's going to go out here.
I think that makes sense. So what would have made me more happy is that if you did this numerics in the other direction, such that we have the dashed line that says, okay, I certainly have to have a twist gap that can't be bigger than that, but also I've had a bound that says I can't get down to zero, and the kink is in some sense on the other side of the dashed black line.
I see.
Then I would have said, oh yes, I can't have a theory, but there's a barrier for me getting to an arbitrarily small twist gap, and so I'm going to find a new theory that has this finite twist gap, and the kink is in some sense in the other direction. So that
Okay, but the numerics is always like it always find
right,
so it's convex.
That's right.
So it's yeah, you're never gonna find something
so
like
the
this.
dream, which apparently is not true for this plot, but from the other plots, the dream is that if you were to push the numerics, that kind of kink-like structure you get would descend below the dashed black line and then correspond to that there would be the theory with that.
But already with 50 derivatives, it's very hard. It should be. I looked at yesterday. It should be 500 to go below. It's
but isn't it true that if you just take a product of two theories without adding any interaction, the theory is going to have zero twist gap because it will have multiples by standards.
Yeah.
So the zero twist gap is definitely allowed. It's in the allowed region.
Right, and so I think what I was hoping is that Fibonacci would exclude that.
No, we take two copies of Fibonacci theories, take a direct product of them.
Like 2 copies of easing.
Two
Ultra-critical easing. Sorry.
Okay. If you don't perturb it in any way, then you're going to come 0.
I see.
Because it's Fibonacci times Fibonacci.
So you're saying if I just two totally separate theories, each one of them has a twist gap, but then I just take their direct product, then I'm guaranteed to have 0 twist gap because I have the second twist stress on 3 times.
Yeah.
And but that's the construction you want to exclude, or that's not the one you're interested in. You're interested in the theory that has nothing beyond, or that doesn't have any additional observed currents.
Yes, precise. No 0 twist gap.
Right.
If I can just add, yeah. I mean, whenever you don't put a twist gap, all the numeric is going to be dominated by theories with conserved currents. So whenever you don't put these things manually, then your numerics, you're going to see lots of things which are corresponding to copies of the critical, or otherwise doing a Witten model. So that's why we really need to do this in order to see something that we're looking for.
Mm-hmm.
Yeah, that's what I was saying. Like if you plot just the scalar gap, that is basically what Lin and Shao did, then they find kinks. They're really nice, but they're saturated by rational theories.
Mm-hmm.
Okay, so as a last thing, I want to tell you what happens for this symmetry. So 2 copies of Fibonacci similarity is 2. We did a lot of work on it. There was this conjecture at the beginning that there may be a theory with central charge 1.77. And what are we finding for this kind of symmetry once we computed all these summaries? So here you can see the results of the comparison with the no symmetry case with the case of symmetries. Now it's really hard for the numerics. It's really slower because of the gigantic system of equations. There is still a region that seems to get sharper and sharper as one increases the number of derivatives, as one improves the numerics, right? It seems to be created. But with respect to the Fibonacci case that was sort of here, it's shifted. Again, we're really above the bound, and now the numerics is even more difficult. So what is it happening when we go below? Is it gonna also shift? Is it gonna survive? And what about 1.77? Because right now we can't see anything. Now, for this kind of symmetry, there is, however, another card that we can play, namely exploit the work that Antonio Antunes and John Jerome did on the lattice. Because we can do this game of inserting the lines also on the lattice. They use another kind of numerics to extract the lowest operators on the spectrum in each of these 22 subinverse spaces. So, and then in our numerics, we can impose that each of these 22 partition functions should have these operators that are found from the lattice. So operators with this conformal dimension and this thing. So we're gonna put it in the normalization, really impose it by hand strongly. And this is something we're doing. Still no results on this point. Our hope is to see that this region is gonna shrink around 1.7. If not, well, it may not be an rational theory. They're gambling on it, if it's rational or not, is one question. So,
but that theory is still allowed, right?
It's still allowed, indeed. So it does. We can't say anything, but for now it's allowed. But for now, everything is allowed.
Is the top is not constraining enough.
Indeed, that's why maybe adding more constraints, such as the lowest operators on the spectrum that are found from the lattice, so from their point of view, will help us to constrain more and see what happens around the region. Maybe not, maybe it's still not constraining enough. So we saw even for like why this, what we saw from the scalar gap against the central charge, even for a rational known theory, such as, I don't know, 2 copies of the critical easing, if you do Fibonacci, then these boundaries did not constrain enough. You're still not finding a kink for it. But if you start putting in a normalization some the lowest operators to the spectrum, then it was shrinking around the correct central charge. So our hope is that maybe it can help also doing this thing. So let me now conclude. We worked it out of the sum rules. We played this fusion category game. It was really fun. We discovered a lot of things otherwise we wouldn't. We built a gigantic system of equations. Then we gave it to the linear programming algorithm for the numerical bootstrap. Preliminary conclusion, it's really hard. They appear to hide themselves well. We're seeing some features. We're really still studying them. We're not really understanding them. And so we're going to study them more. We're going to indeed do this study again around the central charge 1.77, also with the lattice, to see what can. And so a lot of questions for sure. It's a really hard problem, but we're happy there are also other people working on it and try to see. Maybe it's really just too hard. Maybe they can't be constructed from conjectures like this. So it's just a lot of open questions. But for sure, we were seeing interesting features that is nice to explore more. And I'm done. Thank you.
Thank you very much. Are there maybe another couple of questions or comments?
You mentioned several times you have a gigantic system of equations, but you have an intuition of which of these equations are the most important ones.
We think the first, so the one that where the identity is. So you have 22 partition functions, right? And we think that the most important is always the first, so it's the one that contains the identity.
Which is,
for example, for Fibonacci.
People used in the past, or is it a little bit different because of matching?
Sorry, repeat it.
I was just wondering that this equation that you say is most important. Is it
No, we're
possible
saying
to
that
impose it separately from all the other equations? You think it's most important? Maybe you just pose that one, see what happens. Can push the numerics further, or just one equation.
Yeah, no, we try to reduce more the number of equations because it's actually possible. So we actually, I didn't mention, but there are ways in which we can reduce more this number of equations. For example, now actually it's possible to work with this instead of 22 with 12, 13. So it's already way less. And then we tried also to explore separate sectors. It seems that there are more stuff in the first sector, so whenever you have the identity on the left-hand side, but I can't say.
You build this nice machine where it would be nice to see more plots, not just like this particular plot twist cap. It contains no information.
I know.
You should you should make plots which relate, like you have access to all these different sectors of the Hilbert space, which contain interesting information about like the lowest dimension operator and which how like can you say if there is an operator in this sector, then necessarily it has to be operator in that sector, like to show that all the sectors they talk to each other. Otherwise it's just a black box.
I know right now it's really preliminary, but we're working on several sides. And also thank you also for the suggestions. We're exploring a lot.
Can I make sure I understand this? So, like, for example, what they can imagine doing is putting a bound on like the lightest scale operator. But you could say, I want to put a bound on the lightest operator that is in a particular sector.
For example, let's function operator in another sector.
So now what we're doing So now what we're doing is indeed exploring. So you can see that all these features seem to appear around central charge 1.1. So now it's a thing we're doing, but we just started 2 days ago to fix the central charge and trying to explore, so putting a scalar graph. Actually, the region indeed reduces more. Otherwise, and it tells us information that from just this plot we don't have. So putting a bound on the first scalar operator after the identity. So in the first sector indeed, because this is the one in which we can extract more information, and then plotting the sort of 3D plot, but now just for one single charge we did it. We're gonna scan more. And in these constraints more, there are again features, like hills that appear. So yeah.
Okay, so if no other question, let's thank Maddalena again.
Thank you.
And we resume in 12 minutes.